Hello, so before we start doing any differentiation in this video today, I just want to talk about some facts about functions. So if we let f be an injective function on some domain, I'll just call it capital D. Then that means that we've got a defined inverse. So therefore we've got a defined inverse. And therefore, if f is a function of x, then that means that f minus 1, so the inverse function of f of x, is going to be equal to just the variable x. So that's kind of what we mean by an inverse function. So the inverse function maps the original function to the variable that we inserted in the original function. So we know that fact. But how about this? So let's say we've got a new function. So new function g of x. So is it true? So is it true that, let me write that again. So is it true that the following holds? So f minus 1 of f of g of x is equal to g of x. So is that fact true? And I put a question mark up there. So sometimes it is and sometimes it isn't. So it all depends on the range of this function g of x. So the key point here is that this is true, yes, only if the following is true. So in order for us to have a defined function, we need to make sure that the range of values of this g function is a subset of the domain of this f function. So let's just spell this out here. So I mean, if you think about it, if you've got a function which is only defined between, let's say, minus 1 and 1, and this is the f function, so this could be y equals f of x, then if you put g of x into this f function, f of g of x like so, and let's say that g of x ranges between, let's say, -2 and +2, then the issue here is that you've got a range between -2 and +2 for this g of x, but the f function is only defined between -1 and 1, and so this f of g of x won't actually work. It won't actually be defined. So we've got to check for certain that the range of this g of x function is contained within the domain of this f function. So let me just move this this diagram up to up here. I'll just also shift this across as well. Move that up there as well. I'll move the I back down to back down to there. Okay, cool. Yeah. So yes, only if, so this is true only if the range of G is a subset of the domain of F. So the range of G could be equal to the domain of F, or it could be a proper subset of the domain of F. So we know by just basic function facts as well that the domain of a function is exactly the same as the range of its inverse, if f is an injective function, of course. So range of inverse. So basically, this result is true only if the range of this g function is contained within the range of this f inverse function. So that's just a fact that may be useful for later on in the video. But let's go on and differentiate the function that we want to. So this video is going to be about differentiating the function arcsin of 1 over x. So that's what we want to do in this video today. I guess the first key point to mention is that we can clearly see that x can't be equal to 0, because if x was equal to 0, 1 divided by 0 inside that arcsin function would be undefined. So we know that. And in fact, let's just check what this arcsin of 1 over x function roughly represents in terms of its domain and range. So to do that, we can sketch a graph of y equals arcsin of x. We know that if we sketch this graph, so this function is the inverse of the sine function. When we restrict the domain of the sine function, and we restrict it between minus pi over 2 and pi over 2. So the inverse function of the sine with the restricted domain kind of looks something like this. So you have a domain between -1 and +1. You have a range from negative pi over 2 up to pi over 2. So let's just make a note of this. So the domain for this function, so domain is -1 and 1. I'm just going to use, I mean, I should really use closed brackets, square brackets, because the function could be defined exactly at x equals -1 and x equals 1. I'm actually just going to use open brackets just to keep everything easier when we actually differentiate the function here, and you'll see why soon. So the domain is -1 to 1, and the range of this function is minus pi over 2 up to pi over 2. Okay, so we know that, but obviously this video is about differentiating arcsin of 1 over x. So if we just want to analyze the domain and range of arcsin of 1 over x, let's just make this a little bit smaller. So arcsin of 1 over x, let's just write this down here. Well, we know that if the domain of arcsin is between -1 and 1, so in other words, the modulus of x is less than 1, is essentially what we're saying there, then the domain for this function is just the same as the modulus of 1 over x must be less than 1. So in other words then, I mean, the modulus of 1 is just the number 1. So this is exactly equivalent to saying 1 over the modulus of x must be less than 1. And I mean, that's all just equivalent to saying the modulus of x must be greater than 1. So let's make a note of that there. So this is exactly the same, saying the modulus of x is greater than 1, like that there. So I mean, yeah, so x obviously can't be equal to 0 because x equals 0 means the modulus is less than 1. So I mean, yeah, this holds true obviously, because the domain for this function must be the modulus of x is greater than 1. Okay, and in terms of the range, I mean, the range of a function doesn't change when you make a transformation to the variable. It still remains the same, so the range is still going to be negative pi over 2 up to pi over 2. Okay, so we know that information. So that, again, that may be useful for later on in the video. So we're just going to now differentiate this function as we want to do in this video. So we're differentiating with respect to x, the arcsin of 1 over x function. As you'll probably notice, we've got a function, and I'll call this function f, of a function g, so the 1 over x function, and 1 over x is a function of x itself. So this is going to be a chain rule problem. So we know from the chain rule, we've done a few examples of this before. So the chain rule says that when you differentiate with respect to x, a function of x, you get df by dg. So the f function with respect to the g function multiplied by the derivative of the g function with respect to the x function, like that. So we can just apply this chain rule. And if we do so, we get something like this. So arcsin of 1 over x in there. And we multiply this by the derivative of 1 over x, but with respect to x. Okay, great. So we get that. And now we can actually go on and start differentiating this function, because we actually know how to differentiate these functions from previous videos. Sorry, let me just make the writing a little bit smaller. So starting off with this arcsin of 1 over x function with respect to 1 over x. Well, we know from a previous video, because this is a derivative that we did in a previous video. So we know that when we differentiate arcsin of x, we know the result is this. So 1 over the square root of 1 minus x squared. And that was the result that we got when we differentiated this function. But we don't want to differentiate it with respect to x with a variable of x. We want to differentiate it as a variable or as a function of 1 over x with respect to 1 over x. We can just swap the variables here. So 1 over x inside there, a 1 over x inside there. And that means we can just swap the x in the answer with a 1 over x. So 1 over x all squared in there like that. Okay, great. And we can just simplify this a little bit. So we get 1 over the square root of 1 minus 1 over x squared, like so. Okay, so that's our result for the first bit. So we're going to get 1 over the square root of 1 minus 1 over x squared, like that. And then we're going to multiply it by the derivative of this 1 over x function. So we know that 1 over x is just the same as x to the power minus 1. So we can just use the result from our from my first video that I ever did on this channel. We can just bring the power to the front, take away 1 from the power, and then that's our answer. So bring the power to the front, we're going to get a minus sign. Take away 1 from the power, we get a negative 2 in the power, but that's just the same as 1 over x squared. So we get negative 1 over x squared there. Perfect. Yep. So now we can go to a new page, multiply the two fractions together. So top times top, bottom times bottom. And if we do that, we will get negative 1 over x squared multiplied by the square root of 1 minus 1 over x squared, like that. Okay, so now we can actually do a bit of simplification. So if we just bring out a factor of 1 over x squared from inside that square root, like so, we will get x squared there minus a 1 there. Okay, that's fine so far. And then again, if we just bring out this 1 over x squared from outside of this square root into two different square roots, we get negative 1 over x squared multiplied by the square root of 1 over x squared multiplied by the square root of x squared minus 1, like so. Okay, so we know that the square root of 1 is just 1, because this is the same as the square root of 1 over the square root of x squared. So square root of 1 is just 1, so we can leave that there. And in fact, we're multiplying 1 by x squared over there. So we can just get rid of that 1 and move this x squared over there like that. This square root, I'm just going to move up a little bit like that. Yep. And then, okay, so we've got the square root of x squared on the bottom there. Let me just make this all a little bit smaller again. Okay, so the square root of x squared, well, that by definition is the same as the modulus of x squared. So the definition of the modulus function is the square root of x squared. So this on the bottom is actually we've got minus 1 on the top over x squared divided by the modulus of x there, and then multiplied by the square root of x squared minus 1. And okay, so we know also then that the modulus of x squared equals x squared. So we've got the modulus of x times by the modulus of x equals x squared. And so therefore, the modulus of x is exactly the same as x squared over the modulus of x. And so therefore, this kind of factor on the bottom is just going to simplify to the modulus of x. So negative 1 on the top, modulus x on the bottom, multiplied by the square root of x squared minus 1, like so. And so in conclusion then, what we can say is that when we differentiate the function arc sine of 1 over x, we get -1 over the modulus of x times by the square root of x squared minus 1. So yeah, this is the key result that I wanted to show today. However, if you saw the last video that I did yesterday on this, what you may notice is that when we differentiated yesterday the function, so the function arc cosec of x, we got exactly the same result. So -1 over the modulus of x multiplied by the square root of x squared minus 1. Okay, so we got the same result. So a natural question to ask would be, so does that mean that these two functions inside here, so the arc sine of 1 over x function and the arc cosec function, are they the same function? So just because you've got the same derivative, two functions which have the same derivative, doesn't necessarily mean they are the same function. So, I mean, if you think about it, you could have a function such as y equals x squared. So let's sketch that graph roughly like that. And then you could have a function y equals x squared minus 2, but they have exactly the same derivative, but they aren't the same function. So just because a function has the same derivative doesn't mean they are the same function. And also you can have a function which has the same derivative, but may be defined on different parts of the domain. So you could have a part of a function which goes from -1 to 1, and then another part of the function which goes over here, may have a derivative like that. And you may have a function which goes like that, or something that goes like that in the middle. So yeah, so this function is obviously defined on different parts of the domain, on 3 different parts of the domain of the real numbers. So yeah, so just because the derivative of 2 functions is the same doesn't mean that those 2 functions are the same, because the 2 functions could be defined on different parts of the real numbers. So that's the key point from here. So I guess we could try and determine, is this arc sine of 1 over x function the same as this arc cosec of x function? So we can do that now. So we know they've got the same derivative. I guess if we just first of all check, have they got the same domain? We can do that. So we know that the domain of the arc sine of 1 over x function is the modulus of x is greater than 1. Okay, so we know that. So let's make a note of this here. So domain for this arc sine of 1 over x function is modulus of x greater than 1, which we showed earlier in the video. So what's the domain of this arc cosec function? So you may remember from the previous video that we did that it is also the modulus of x is greater than 1. So if we try and like draw a graph of arc cosec, so it looks kind of like this. We did this in the previous video. So y equals arc cosec of x. So yeah, something like this. So tending to 0 as x tends to infinity, and tending to 0 as x tends to negative infinity, something like that. You've got 1 there, you've got pi over 2 up there, and you've got -1 there, and negative pi over 2 on the y-axis, like that. So that is what the arc cosec function looked like from the previous video. And again, we can clearly see that the domain is, as we just said on the previous slide, so the domain is modulus of x greater than 1. So we've got 2 functions with the same derivative. They've got the same domain. So we can clearly state that they are the same function up to a constant. So let's just write this here. So same domain and same derivative. So that implies that arc cosec of 1 over x is the same as arc sine. Sorry, I've made a mistake here. Sorry, this should be arc cosec of x is the same as arc sine of 1 over x up to a constant, so plus a constant c, because as we showed here, you could still have like an extra constant if it is defined on the same domain. Okay, so let's find out what this constant is. Well, it's actually going to be 0, but let's try and prove that. So if we just make this a little bit smaller again and move that up there. Okay, so to find out what this is and to find out whether indeed these two functions are the same, what we can do is just let y be equal to arc cosec of x. And then what we can do to both sides is apply the cosec function, which is the inverse of the arc cosec function. So we get cosec of y equals, so cosec of arc cosec of x, but we know that this is just going to be x. And the reason why is because we can go back to the first slide here. When you take the inverse function of a function of x, the result is the function of x. Sorry, the result is the variable x. So we know for a fact that this is just going to be x there. So cosec of y equals x. Now we know by definition what cosec is. So cosec is just the same as 1 over sine. So this is the same as 1 over sine y, and this equals x. We can just rearrange this to make sine y the subject of the formula. So we're going to get sine y equals 1 over x like that. And then what we could do to both sides, we could try and apply the arcsine function to both sides. So arcsine of y, and that equals arcsine of 1 over x. Okay, so we've got that. So now you may be thinking, okay, well, arcsine and sine, they're just inverse functions. So surely this just equals y. However, we've got to be careful. So yeah, if y was a variable, so if sine was a function of the variable y, then yeah, this would be correct here. But we've got to be careful because y is actually a function. So this y there is actually a function of x. So let's make this clear that this y is a function. So that means that we have to use this rule back at the start of the video. So the inverse function of the original function of a new function of x is only equal to the new function if and only if the range of this new function is contained or is a subset of the range of the inverse function. So let's write this out here. And we're going to make this all a little bit smaller again, just to try and keep it on the same page. Okay, so we need to check. So need to check is the domain of y. So is the domain of y contained in the, sorry, not the domain, my bad. So is the range of y, because we're looking at the range of y values that we can insert into the sine function. So is the range of y contained within the domain of sine? But the domain of sine is just the same as the range of arcsine. So I'm just going to write arcsine there. So range of arcsine of x. So the range of this y function, well, y is the arc cosec function, isn't it? And we sketch this graph over here. And we can see that the range is between, so minus pi over 2 to pi over 2. So the range is minus pi over 2 to pi over 2. So let's write that down here. So the range of y, so range of y of x. So just to make this clear, y is a function of x. So the range of y of x is equal to minus pi over 2 up to pi over 2. And the range of arcsine, so we did this back at the start of the video over here. Yeah, so the range of the arcsine function we can see is also minus pi over 2 up to pi over 2. So let's make a note of this. So minus pi over 2 up to pi over 2. And so therefore, so let me just make this clear here. So this range here is the same as the range of arcsin. So range of arcsin of x. And so, okay, so they've got the same range. So what that means is that indeed the range of y is a subset of the range of the inverse function, so the arcsin function, because if they are the same function, then it's still a subset of the other function. So therefore, range of y is a subset of range of arcsin, and so therefore it must be true that arcsin of sine of y is equal to y. So therefore, arcsin of sine of y of x is indeed equal to just y. And we know from the right-hand side that y is equal to arcsin of 1 over x. So y equals arcsin of 1 over x. But we know from up here that y is equal to arc cosec of x. So therefore, we can just conclude from this that arc sine of 1 over x is equal to arc cosec of x, like that. So they are indeed the same function. So obviously they are going to have the same derivative. And yeah, of course, they're defined on the same domain too, as we showed over here. So yeah, so what that means then, let's just write this on a new page, is that the derivative of arcsin of 1 over x is the same as the derivative of arc cosec of x. And so therefore, the result we got was -1 over the modulus of x multiplied by the square root of x squared minus 1. And yep, that's the result for this video today.